So, so this is all about uh, moment of inertia. Okay. So, as regarding this relationship, which I explained between F is equals to ma and m is equals to I alpha, is there anything which is not clear to anybody? You can ask. Is the concept so far clear or not? Okay, so let me just repeat what I have already said one more time. It will take me 2-3 minutes. But right now we are discussing chapter number 17. Chapter number 17 is similar to chapter number 13, and in 13 we started the kinetics of uh, particles. So here we are going to start the kinetics of the rigid bodies. And since chapter number 13 was the force acceleration method, so here we have chapter number 17, which is also kind of a force acceleration method, but not for the case of particle. We will be dealing with the solid bodies. Okay, so since we are dealing with the solid bodies, so here in case of the particle, there was no rotation. So rotation factor was not there. But here, in case of the solid bodies, we have we have specific bodies which have a specific shape and size and occupy specific volume. So these things can rotate. Solid bodies can rotate. So when you have the possibility for the solid bodies to rotate, so now we need to consider, along with the linear motion, also the angular motion. This is now something that needs to be considered as well. So in chapter number 13, we were only discussing the linear motion. Now we need to discuss the linear motion as well. Along with it, we also need to consider the angular motion. So for the case of linear motion, the most common equation that we have been using is the Newton's second law of motion, which is F is equals to ma. Okay, so we have been using this equation quite long for a long time. And this was the equation which is, since it's a force acceleration method, we studied it a lot in chapter number 13 as well. So here we are going to still study the force acceleration method. So, but since we will be studying the force acceleration method, so we have to use F is equals to ma. But along with that F is equals to ma, we also need to study the equation in the angular format. Okay, so in the angular format, we need to have an equation which is very analogous, which is very similar to the linear motion equation. So the similarity could be seen here, that we have so instead of force was something which was causing the linear motion. We have the moment is something which tends to produce the angular motion. And uh, a was the linear acceleration, so linear motion itself. So instead of a, we are going to have alpha, which is the angular motion, which is the angular acceleration. And m was basically what it could be considered as the resistance to the linear motion, because there's a regular understanding that uh, if m is high, then the producing the motion would be difficult. So something is heavier, it's hard to produce motion in something which is heavier compared to something which is lighter. So m is kind of a resistance to motion. So since mass is the resistance to the linear motion, we also need to have a resistance to the angular motion. And that resistance to the angular motion is known as moment of inertia. Okay, so here we have, instead of m is equals to ma, we have a moment is equals to I into alpha. So this is the analogous relationship between uh, between the linear motion and the angular motion. And remember, in chapter number 13, we were studying F is equals to ma only, but here in this chapter, F is equals to ma is still applicable, but along with that, we will also have m equals to I alpha, uh, which is the angular motion. So anyways, If anybody has anything not clear so far, you can ask. Otherwise, I can move forward. Okay, so before moving to study the, the kinetics for the case of solid bodies, we need to first study the moment of inertia I, because mass was a simple thing. Mass was a simple thing. So a body has a specific mass, so it's a property of the body. Okay, but moment of inertia is a little more complicated thing compared to the mass. Now moment of inertia is basically what it is. It depends upon how the mass is distributed within the body. It depends upon how the mass is distributed within the body. Okay, so mathematically we represent it as I is equals to r square dm integrated all over m. So we have differential mass, and that differential mass is distributed across the radius r throughout the entire mass of the body, integrated over the entire mass of the body. So r is the moment arm. Okay, so this is the integral format for the moment of inertia. So see, dm is basically the differential mass. We can write it in terms of the volume. So then it will be density into dv. Density, if it is constant, most of the time for solid bodies it is constant. So we can take the density out, and then we can have an integral r squared dv. So differential volume we can write in terms of the distances. So dv could be written as dx dy dz. Then we have triple integration. This will be the triple integration format for the case of for the formulation for moment of inertia. The units for the moment of inertia would be kg meter square. Now let's study something about the moment of inertia. Let's take an example. For example, so we can write in the in the differential format, or the integral format, we can write it as I is equals to integral r squared dm. But if we want to write in the discrete format, we are going to write it as I is equals to summation miri square. uh, I don't know whether you have the concept between summation and integration. So uh, there's a relationship between summation and integration. Integration, if something is varying, uh, if something is varying analogously. So if there is an analog data which is varying like that, then you need to integrate it. It needs to be represented in the form of an equation, and then it needs to be integrated. So that is integration. The similar way we have summation. Summation is if if something is not analogous, rather discrete. So for discrete things, when you have to add them up, so it is just the summation. So I don't know whether you have the real concept between summation or integration or not. But suppose if something is like this, so it is an analogous line. So analogous line, you need to have an equation of the analogous line, and then you need to integrate the equation. But suppose if something is like this, so this is discrete. We have constant values, multiple constant values. So for multiple constant values, when you need to integrate them, so it's in mathematics we generally represented as summation. So anyways, I was just trying to explain that this formula written here, I is equals to integral r squared dm, is the same formula as summation miri square. But this is for the case when the radius is varying analogously. And this is for the case when the mass is distributed along the radius discretely. So suppose I have a body like this. Suppose this is the body that I have, and this body have discretely mass distributed. Let's say m mass is here, 2m mass is here, 3m mass is here, 4m mass is here. Okay, so if I need to find the moment of inertia about this axis, if I need to find the moment of inertia about this axis, then it will be summation MIRI square. Okay, so this mass, so if this length is 2a, and let's say this length is a, so this mass multiplied by the radius here will be a, so ma square plus 2ma square plus 3ma square plus 4ma square. So if you sum up all, it will be 10ma square. Okay, so let's call this as capital Ma square. Okay, now let us suppose that we have this same object and we need to find the moment of inertia for it, but instead of finding the moment of inertia for it along this axis of rotation, we want to find the moment of inertia along this axis of rotation. Okay, so suppose for the same object, now we are finding the moment of inertia for this same object along this axis of rotation. So here it is total A, this is 2A, so it's summation MIRI square. So M, so this will be what? M into A by 2 plus 2M into A by 2 plus 3M into A by 2 plus 4M into A by 2 square. So it will be 10 by 4MA square. Now, if you look at it, this is the same object. This is the same object. I'm not changing the object. The object is same. Like here, if we go into the previous slide, this is the same object. M, 2M, 4M, 3M. M, 2M, 4M, 3M. That's the same object. But if you change the axis of rotation, the moment of inertia is different. So here the moment of inertia was 10 ma square. Here the moment of inertia is 10 by 4 ma square. The moment of inertia is the resistance to angular motion. Resistance to angular motion means here, when you want to rotate this object along this axis, so it is 10 ma square. So, and when you want to rotate this object along this axis, it is 10 by 4 ma square, means moment of inertia or the resistance to rotation in this direction is 4 times less than the resistance to rotation in this direction. So this means if we talk about the mass, so overall mass for this object is the same whether you are rotating it in this direction or in this direction. Overall mass is not being affected, but the axis of rotation and how the mass is distributed along the axis of rotation, this actually changes the resistance to rotation. So resistance to rotation is not just dependent upon what is the total mass, but it also depends upon that how that mass is being distributed along the axis of rotation. So this is one another parameter which is different from just the linear case. Like for example, we had the mass. In the linear case, we have the mass. So mass is mass. It's total. That's it. So it is the same in any case. But the moment of inertia or the resistance to angular motion is not going to be same. It depends upon the how the mass is being distributed along the axis of rotation. So before moving forward, I don't know whether I tried to explain things, but I don't know whether you are able to understand it, things so far or not. Is there anything anybody want to ask? You can ask. Okay. R is the distance from the axis to one point on the body. Yes, R is basically the distance from the axis of rotation to any point on the body. Right now we are considering a body with discrete masses. So here this R is the distance from the axis of rotation to this mass, then to this mass, then to this mass, then to this mass. So let's say that we have discrete masses here. So in that case, it is like this. But in generally, if we don't have a discrete mass, but if the mass is entirely divided, uniformly divided throughout the entire body, then you cannot use this formulation, this summation formulation. We have to move back to the integral form of the equation. Okay. So there is a huge concept of, dynamics is basically a kind of a course where you cannot really separate mathematics out of it. So all the concepts of mathematics, advanced mathematics, differentiation, integration, summation, uh, it's hard to give all those concepts during the course, but it is considered that you have those concepts before while you are taking this course. So anyways, if you have better concepts in mathematics, things becomes more easy for you to understand in this course. Otherwise, you need to struggle a bit. Okay, so suppose I have a continuous body with the continuous mass distributed along the entire body. Then in that case, I cannot use the discrete formation, and rather than that, I will have to use the continuous formation or the analog formation of the formulation. So in that case, I need dv. So it depends that what kind of differential volume I can take. So I can take the shell element. Let's say I can take a differential volume as a shell. So if I take it as a shell, so shell means you have a cylindrical body. Okay, so it's 2 pi y. Let's say that the radius is y. Okay, and then after that, for the cylinder, you will, let's say that the length of the cylinder is z. So it's 2 pi y z dy. So y is going to change, differentially change, and it's going to change until it cover the whole body. So this is how we take the shell element. And suppose if we don't want to take the shell element, we can take another type of element, which is the disk element. In case of disk element, it should be the area of the disk, which should be pi y square. Let's say y is the radius of this disk. Okay, multiply by dz. Let's say dz is the thickness of the disk, and in that case, then 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 this element dz is going to vary throughout the entire body until we integrate it over the entire body to get the entire volume. So anyways, so these are the two possibilities that we can solve the problems for finding the moment of inertia, either using the shell element or the disk element. So other than that, we have some regular shapes. For those regular shapes, the moment of inertia is predetermined. If these are the basics regular shapes, then the moment of inertia for these are predetermined, and we can use those predetermined formulas, and we can consider these shapes as the discrete shapes, and like the discrete bodies, where we can use the summation formulation. As I told you, summation can be used for the discrete objects. So suppose if we have a thin rod, so thin rod could be behaved as a discrete object, as a separate object. Okay, and for the case of a thin rod, if the axis of rotation is in the center of the thin rod, it will be I is equals to half, 1 by 12 ml square, where ml will be the mass of this rod and L will be the overall length of the rod. If it is the same thin rod, but the axis of rotation is not in the center, rather it is at one end, then in that case, the moment of inertia, again, this object could be considered as a discrete object, and moment of inertia would be I is equals to 1 by 3 ml square. If it is a solid disk, then solid disk will have, let's say this solid disk has a radius r, and its axis of rotation is like in the center here. So then I is equals to half mr square. If it is a hollow disk, okay, so we'll have two radiuses here, one inner radius, other outer radius. So for the case of a hollow disk, again, we can consider this hollow disk as a discrete object, and the moment of inertia formula is already calculated, provided to you. I is equals to half mr1 square plus r2 square. Suppose if it is a rectangular plate, and the axis of rotation is through the center. So we have two sides of the plate, A and B. So we can write the moment of inertia as 1 upon 12 m a square plus b square. Okay, why I'm going through all these formulas and all these shapes with you, because this formula sheet, this page will be provided to you in the exam, and I can bring any shape out of this. Okay, when we'll be solving the problem, you can see that I can bring any shape out of this. The formulas will be in front of you. You should be able to use these formulas to find out the moment of inertia. So I is equals to 1 by 12 m a square plus b square. So if it is a thin rectangular plate, but not rotation, axis of rotation is not in the center, rather it is at one of the edge like this, then it will be 1 upon 3 m a square. Okay, a, because this a is perpendicular to the edge where it is rotating. Okay, then if suppose if we have a thin walled hollow cylinder. Thin walls, thin wall means the wall is very thin. We will not have R1 and R2, two radiuses. We will have just one radius, R. Okay, so for the thin walled hollow cylinder, the moment of inertia will be I is equals to mr square. Similarly, for the case of the solid sphere, it will be I is equals to 2 by 5 mr square. Let's say that the radius of the sphere is R. And if it is thin walled hollow sphere, okay, then it will be I is equals to 2 by 3 mr square if the radius is R. Okay. Before moving forward and onward, I need to ask, is there anything which is not clear so far in the slide? Okay, the student is asking, should we remember the shell and disk formula? Shell and disk formula, if you mean this, then yes, you should remember this. But if you mean this, so no, these formulas are the moment of inertia formulas. They will be provided to you in the exam. Okay. Okay, these are again, they're the same formulas written, so you can go through them. Okay, now before moving forward, there is another theorem. There's another concept, which is the parallel axis theorem. Now, parallel axis theorem is basically used to find the moment of inertia at any point within the body if we know what is the moment of inertia through the center of gravity of that body. This is the case. So suppose I have a body. Okay, let's say I draw a body. Let's say this is the body. Okay, let's say this is the center of gravity of the body. Okay, if I know what is the moment of inertia across this center of gravity, then I can find, using parallel axis theorem, the moment of inertia across any point on the body. Any point on the body. Let's say if the body is rotating at this point, if the body is rotating at this point, then what is the moment of inertia for this? Okay, so this parallel axis theorem allows me to actually get the moment of inertia, to calculate the moment of inertia from any point on the body if I know that what is the moment of inertia for this object at the center of gravity of this body. So before moving towards understanding the problem, it's understanding the formula itself. First of all, do you understand what is parallel axis theorem? Okay, so let's study this formula. The formula is that we can find I, moment of inertia at any point, which will be equals to Ig, moment of inertia through the center of gravity, plus md square. M is basically the mass of the body. Ig is the moment of inertia for mass center G. M is the mass of the body, and d is the perpendicular distance between the parallel axis. Okay, so remember, let's say this is the center of gravity, so body might rotate across this axis. So if I want to know the center of gravity at this point, so this is a parallel axis. This axis is parallel to the axis through the center of gravity. Okay, so I can find that what is the moment of inertia if the body is rotating along this point. Let's say I call this point as O. Okay, so I can find IO if I know what is IG plus M into D. And D is basically what? It is the perpendicular distance between these parallel axes. So one axis is this, other axis is this. The perpendicular distance between them, this is actually D. Okay. Things will be much more clear to you when we are going to start solving a problem. Okay. One student is asking, can you please repeat? So can you please specify what is the thing that you want me to repeat? Okay, good. So far, students, are you with me? Are you understanding whatever we are trying to go through? Okay, good. Okay, so next is the concept is the radius of gyration. Now, radius of gyration is basically what? This is again another concept that we will be using in this chapter. So, first of all, radius of gyration has a formula I is equals to mk square, where k is basically the radius of gyration, and it could be written as k is equals to I upon m integral uh, under root. Sorry. So, radius of gyration, it's quite a more complicated concept. Okay, the things get more clarity and understanding when you actually watch the radius of gyration or the motion of the body, or the variation in the motion of the body with the change in the radius of gyration. So this is a quite more complicated concept. In generally, basically you see we have an axis of rotation, and the mass of the body is distributed across the axis of the rotation. Okay, but most of the time the mass is not evenly distributed. Okay, but suppose if we have an imaginary radius across which the mass is such evenly distributed that it produce the same moment of inertia or resistance to angular motion as the actual body is producing, then that specific radius, that imaginary radius, is known as the radius of gyration. uh, I don't know whether you understood or you were able to catch up with me or not. This is a bit more complicated concept, but let me repeat again that radius of gyration is an imaginary radius for any object. Okay, so most of the time when an object is rotating, so the mass of the object is not evenly distributed. Okay, so if we want that, suppose there is an imaginary radius across which the mass is such evenly distributed that it produces the same moment of inertia, same resistance to angular motion as the actual body, then that imaginary radius is the radius of gyration. And it has a huge application in the vibration industry, in the industry where you're generating motors, wherever the objects are rotating at a very high speed, most of the time heavy machinery, heavy engines. Okay, now you see you can go and sit in a very advanced car and the engine is rotating at a very high speed, but you feel nothing. Okay, you are sitting in the engine and you don't feel any vibration, and everything is so smooth. Even when the car is running on a very rough road, it's still the car is very smooth. So how is that? So there's a huge lot calculation, there's a huge lot application of this radius of gyration in the design of the rotating objects, in the design of the machinery. Anyways, we are not going to go into that detail. Normally, those who study this mechanics and the vibration, they go into much more detail. Just at this point, I wanted to give you a little concept about it. So, is it clear so far? Okay. Okay. Then, other than that, we have another concept, which is the mass center. Now, how do we find the mass center? suppose I have I have a body. Let's say this is a pendulum. In this pendulum, it is made up of two thin rods. Okay, so I have this one thin rod, then I have another thin rod. Okay, these two thin rods make up or join together to make up this pendulum. Okay, if I consider this thin rod alone, then I can clearly see that the center of this thin rod would be here. Okay, if I consider this thin rod alone, then I can see that the center of this thin rod would be here. But if I consider this whole body, combination of these two thin rods, if I consider this whole body, then how would I find the mass center? The mass center will not be this, it will not be this as well. Okay, this is a combination of two discrete objects, two thin rods. This is one thin rod OA, another thin rod BC. OA and BC are connected together to make this object. OA has a center here. It's very clear. It's a thin rod discrete object, very simple object. So one can see that its center would, mass center would be the center of this thin rod. BC is again a thin rod. So one can see that the mass center for this thin rod would again be at the center of this. But if I consider the combination of these two simple bodies, these two discrete objects, then this makes up this pendulum. But we also need to know the mass center for this pendulum. The mass center for this pendulum will not be this and will not be this as well. So how do we determine the mass center of this object? So this is a complicated object which is made up of simple discrete objects. Okay, so the formulation for it is y bar is equals to summation summation ym divided by summation m. So here, how would we deal with this? Y is basically, so here we have summation here. So we have two objects. One object, both objects mass are provided. Let's say this is 10 pounds. The other is also 10 pounds. So this will be 10 by 32 by 2, 10 by 32 by 2. Okay, so if we consider from the top edge, okay, so y bar, so into m for this specific object. So here this will be the center of it. Since this is 2 feet, center of it will be 1 foot. So this will be 1 foot. Okay, and if we consider the center for this BC from our reference point, so that will be 2 feet. So this will be 2 feet here for the second rod. Okay, divided by summation of masses. Okay, so 10 by 32.2 plus 10 by 32.2. So this will give us the y bar for this entire complex object, which will be 1.5 feet. Okay, so from this reference point, from the same reference point, it will be at 1.5 feet for the mass center for the whole body.
Doctor,
Yes.
it's not clear of the one and two. Why we calculate the BC is two and OA is one?
Okay, look, for BC, we always need to take a reference point. Suppose if we take this as the reference point, okay, let's say this as the reference point. So we need to find the distance of the mass center for each simple body from the reference point. So mass center for BC will be here, and the distance from the reference point will be 2 feet. Is it clear?
Yes, it's
Okay,
clear.
and the mass
So
center and mass center for OA will be here in the center, and the distance from the reference point will be because total is 2 feet, so it will be at the center 1 feet. Is the concept clear?
yes, clear. Uh, we could say the one is the distance between B and A from A to B multiplied by OA, the force mass of OA, right?
You confused me actually. I don't know why you say A to B. One object is OA, other object is BC.
It's same calculate the moment
Yes.
distance by mass, distance by force, but we We calculate distance by mass, or not?
No, I think you're not getting it.
Okay.
So
Oh,
this is mass center. We are not talking about force anything about in here. We are just trying to figure out what is the mass center for this entire object. Okay, so the mass center for this entire object would be summation of mass center for individual objects divided by summation of the masses. Okay, so summation of the mass center multiplied by the mass of the individual objects divided by summation of the masses. So we have two masses here. Okay, so let's say our reference point is, so let's say this is our reference point. Okay, so mass center for OA will be here in the center, right? So if this is 2 feet, so the center will be 1 foot. Okay, so that will be, this distance will be 1 foot. So 1 foot is here, 1 foot multiplied by the mass of this object, plus mass center for the second object. So second object is BC, its mass center will be here, and the distance from our reference is actually 2 feet. So we just put 2 feet here, multiply by the mass of the second object. So we have summation of mass centers multiplied by the mass divided by summation of masses, summation of individual masses.
so just need in y direction.
Yeah, this
We
is
don't.
for the case of the y direction, because
Okay.
here in, if you see here, this is a mirror image. If you draw a center line, there is a mirror image from here and there. Okay, so one thing is very clear, that for the x-axis it would be in the center, but the y-axis it was not mirror image. If I draw a center line here, so this thing is entirely different from this thing. Okay, so for the y-axis it would be at a different location, but for x-axis it would be in the center. Okay, so here in this problem, we do not need to do it for the x-axis. We just need to do it for the y-axis. So if it was if it was no mirror image here like this, suppose if it was like this, that object is here, instead of joint at the center, if the joint was like this. Okay, so in that case, now we need to do for both, the directions, for the for the y-axis as well, and let's say for the x-axis as well. So for x-axis, we take this as the reference. For y-axis, we take this as the reference. So in that case, we need to do it for both. But here for the x-axis, we are sure that this is a mirror image, so it would be in the center. Okay, so we need to find the mass center. The mass center could be in the two-dimensional for two-dimensional objects. It has to be the x-axis and y-axis both. We need to find the exact point G. I hope, I don't know, but I thought that you guys have covered this thing for how to find the mass center in statics. Am I wrong?
Yes, yes, we covered it.
You covered it in statics, right? So I hope that things will be more clear to you. Okay, so let's see a problem here. If the density of the material is 5 slug per feet cube, okay, if the density of the material is 5 slug per feet cube, determine the moment of inertia of the solid in about the y-axis. So you have this object. Now this is not a regular object, so you cannot divide this object into discrete parts. Okay, it's not a thin rod, it's not a hollow cylinder, it's not a sphere, it's not a disk. It's an irregular object. So if you have an irregular object and you need to find the moment of inertia, okay, you cannot use the summation technique. Now you need to move towards the integral format of the solution. Okay, so let's see the solution for it. Okay, so we have this object. Okay, so density of the object is 5 slug per feet cube. Okay, now here we can take is that we can take the disk element. Okay, so disk element, let's say in this the direction, in the y direction, we can take the disk element. So the radius of the disk is basically x. Radius of the disk is x. Okay, and the thickness of the disk is dy. So for the disk element, okay, right now Azan is going on. Let's take a break of 10 minutes. And in this 10 minute, let me pray and then I'll be back. We're going to continue. Okay, we have 1 hour left. Okay. So let's take a break of 10 minutes and then we're going to continue here. Okay. Just after this prayer, I'm going to respond to your question. Okay. So let's have a break of 10 minutes and then we'll be back. Assalamu alaikum, students. Can you hear me?
Walaikum assalam, yes.
Okay. So we started doing this problem number 1. Okay. So in this problem, it was said that okay, if the density of the material is 5 slug per foot cube, determine the moment of inertia of the solid about y-axis. Okay. So we hear this for this solid. We know the equation y is a function of x, or x is a function of y. So y squared is equals to x. And this is 1 feet in the radius and 1 foot in the length. So let's see the problem solution for it. Okay, so we can take the disk element. Okay, yeah, one student asked that shall we how to decide whether to use disk element or shell element. So my only answer is that you can understand this only by experience. So you need to study different type of problems, and then you need to study and you need to judge which type of element would be better. Sometimes a problem is solvable both by shell method as well as by disk method. Okay, so both are possible, but uh, in one of the method it will be a little more difficult, because when you're going to apply the limits of integration, things might get a bit more complicated than one of the method compared to the other method. So this you will only understand by experience, by practice. So it's like chapter number 12, where you have a bunch of formulas and how to decide which formula to use where. Most of the time it's just by experience and practice that you can know. Otherwise there is no direct methodology to think about that. Okay, so here if we take the disk element, it would be more appropriate, more reasonable to do it. Okay, for the disk element, we know that for the disk element, I is equals to half mr squared. That's the moment of inertia. Okay, and we know that for the volume of the disk will be what? The area multiplied by thickness will be pi r square h. But here radius is basically x. So it will be pi x square, and the height is here, it will be dy. So it will be pi x square dy, corresponding to the x's given in the question. Okay, so we have dm is equals to rho dv. That's the differential mass. Okay, so we can use diy is equals to half dmx square. So we can use this formulation. This comes from here. Okay, so since I is equals to half mr square, so diy will be half dmx square. Now dm can be written as rho dv, and dv is dv, we can find it as, because we know that v is pi x square dy. So dv will be pi x square dy. Okay, so this we will write it as dv. V was pi r square h, so dv is pi x square dy. So this is dv. So here it becomes half pi rho x power 4 dy. Okay, So we can move forward here. We can apply integration. Okay, so if we integrate diy, will be pi rho by 2 integral, because now we can substitute x as a function of y, because we know x as a function of y, x is equals to y square. So it will be y power 8 dy. Then we integrate it, it will be y power 9 by 9. So here the density was given, pi is a constant, y we know from 0 to 1, that's the overall length. Okay, so we just need to substitute all the values, you're going to get iy. So we determined what is iy using using the integral format for the equation. So we basically used the moment of inertia for a disk, and then we integrated the disk over the entire body. So we take the moment of inertia for the disk, write it in the differential format, then substitute the values of dv, and then integrate this disk over the entire length of the entire length of the body, so entire y from 0 to 1, and then just substituted the values to get iy. Is there anything which is not clear in the solution of this problem? You can ask.
Doctor, can you repeat how did we start?
How did we start? Look, we know that dm is equals to rho dv. It's basically the mass is density into volume. Okay, so differential mass is equals to rho dv. Okay, so we know this thing. Now how did we start? We started from here. Since we took the disk element, so for the disk element, we know that the formula is I is equals to half mr square. This is for disk element. This is something we know. Now we need to find I for this disk element using this disk element in the differential format while integrating it over the entire body. So first we write in the differential format. This is the same formula written in the differential format. Okay. Then after that, just substituting the value of the volume for this disk element, and then integrated it over the entire length. Do you get it or not?
Yes, thank you.
So so the methodology always will be here, that it always depends upon which kind of element you are going to use. So if you use shell element, then you have to start by writing the moment of inertia for the shell element, and then after that integrating that shell element for the entire body. Or if you're using the disk element, then you need to write the moment of inertia for the disk element in the differential format, then integrating that disk element for the entire body. So this is how we do it. And since here it was possible because this was a continuous body, and so it could not be divided into discrete components, discrete simple components, and we know the equation of y as a function of x or x as a function of y. That's why we were able to do it. Okay, solution is done here as well, but my handwritten solution is better because I wrote all the steps. Here things are done like missing the steps. Okay, so that was for the case of for a case of a problem where we needed to use the differential form of the element and then integrate it over the entire body. But here, let's say that we have another problem, but this problem is a kind of a problem where we do not need to use the integral form of the equation. Rather, we can find the moment of inertia by discretizing the entire object into simple objects, into simple components. So we have a pendulum here. This pendulum consists of 3 kg slender rod. So this is the 3 kg rod. This rod is 3 kg. Okay, and a 5 kg thin plate. So you have a thin plate here, and this is 5 kg. Determine the local y bar of the center of the mass of the pendulum. So first we need to find what is the mass center. First we need to find what is the mass center for this pendulum. Then calculate the moment of inertia of the pendulum about an axis perpendicular to the page and passing through G. So then we need to find IG, but this IG for this whole object. Okay, so this is the main thing. We need to find this IG for this whole object. And so anyways, before moving towards the solution of the problem, first, do you understand the problem statement or not? Is there anything within the problem statement that is not clear? Please ask. Try to understand one thing always. When it is said that calculate the moment of inertia of the pendulum about an axis perpendicular to the page and passing through G, that means if the axis of rotation was G, student get confused sometime, because in the problem which is shown here, in reality the axis of rotation is not at G. In reality the axis of rotation is at O. But here in the question, it is not asked to find the moment of inertia for the axis of rotation at O. It is asked to find the moment of inertia. Suppose if the object was held together, pin connected at G, then what will be the resistance to the rotation of that object? So we need to find the moment of inertia of the pendulum about an axis perpendicular to the page and passing through G, not O. Okay. So anyways, this is the problem statement. If you know, if you don't have any problem in the problem statement itself, then we can move towards the solution. Okay, so this is the thing that we have. First of all, we need to determine the mass center. Okay, this is 3 kg cylinder rod, 5 kg thin plate. Okay, so mass center is y bar is equals to summation yi mi over summation mi. Okay, so for this cylinder rod, okay, it will be, if we take this as our reference point, okay, so it would be because there were the dimension was given there. So this is actually 2 meter, this is 2 meter, and this is 0.5 meter. Okay, so for the cylinder rod, the half would be 1 meter, because this is 2 meter and this is 0.5 meter. So for the cylinder rod, the center of it from the reference would be 1 meter multiplied by the mass 3 kg, plus the center for this plate from the reference would be 2 plus half of 0.5, which will be 0.25. So it will be 2.25 multiplied by the mass of the plate divided by the mass of the rod plus plate, which is 3 plus 5. So the y bar will be 1.781. Before moving forward, is this step so far clear or not? Is there anyone for whom this step is not clear? Okay. So the first thing was that we determined what is the mass center. So the mass center is y bar. Okay. Now let's move ahead. Let's move forward. Okay. So now I need to find IG. So now I need to find IG, but this IG through the center of the whole pendulum, this through the center of this whole pendulum, this G. Now I know the exact location of G, because this exact location of G is from y bar, and this is the y bar, which I have just calculated, 1.781 meter. Okay, so in order to find IG, I can convert this object into two discrete objects, one the cylinder rod, the other is the thin plate. These are two discrete objects. Okay, so I need to do the summation for both the objects at this point IG. Okay, so I need to find the moment of inertia for the cylinder rod, but at IG. This IG is not for the cylinder rod, but for the whole pendulum. When I call here this IG, this IG is for the whole pendulum, not for one object. So, but when I'm saying for here summation IG plus MD square, so this IG is for individual components. So here, for example, we have the cylinder rod, okay, and then we have the thin plate, okay. So this part is for the cylinder rod, and this part is for the thin plate, okay. So here this IG bar will be for the case of cylinder rod. For rod, I is equals to 1 by 12 ml square. So this formula will be provided to you in the exam. So you'll have 1 by 12 m is the mass, L square, plus m, which is the mass, into d. Now d is what? Perpendicular distance for the center of the rod to the center point here. So this distance. So center point here is G, center of the rod is half, okay. So this is 1.781 from this reference, okay. So it will be 1.781 minus 1. Do you understand this thing or not? This is important. If there is anyone who do not understand this, you can ask. I'm asking about this 1.781 minus 1. This is D. This is D for the case of cylinder rod. So it's a perpendicular distance, this distance, because IG for the whole pendulum is here, and the center of mass for this cylinder rod is at the center of it. So since this is 2 meter in totality, so this will be 1 meter, and this IG from the reference point is 1.781. So 1.781 minus 1 is this distance. Is it clear? Okay, so now let's see the other object. The other object is our thin plate. For the thin plate, I is equals to 1 by 12 m a square plus b square. So 1 upon 12 mass into 0.5 is square, a plus 1 is square, because this dimension is 1, this is 0.5. Okay, plus m, which is again the mass, multiply by d. Now the d here will be what? It will be distance from here to the center here, this distance, okay. So the total, if we take from this reference, so total from this reference to the center of this plate will be 2.25 minus 1.78. This is 1.78. So that will be this distance. So once you have this thing, all of this thing, you just calculate it, and you solve it, and in the end you get the answer of IG. So this is how the solution of this problem done. The problem is solved, but I need to know that do you understand the solution of the problem or not? Is there anything, any step which is not clear? Please ask. Okay. So the answer is 4.45 kg meter square. So the solution is done here as well. This is a practice problem. Solution is there. You can go through it yourself. There's a self-study problem. You can go through these. Okay, so now planar kinetic equation of motion. Okay, this is the next topic here. So previously we used to deal with summation f is equals to ma. Okay, now we are not going to deal with just summation f is equals to ma. Summation f is equals to ma will also be there, but at the same time now we are dealing with solid body, and the solid body can rotate. So here we will have summation of moments equals to ig into alpha. This is something which will also be there. Okay, so the three set of equations that we are going to have here will be in the x direction, summation fx equals to max, summation fy is equals to may. And previously we don't, these two we used to have before, but previously we do not used to have this third equation, which is the summation of moments is equals to ig alpha. Now this is something that we are going to have now as well, along with these two equations. So you see here the old knowledge which used is there and is going to be used here again as well. But along with that old knowledge, since we are discussing about the solid bodies, so the bodies have a specific shape and size and they can rotate. So now we will have an additional equation for the rotation. So an addition is there in if it compared to chapter number 12. But all the equations and the laws that you studied there are equally applicable here as well. So suppose if it is a rectilinear motion. So right now we are discussing about the solid bodies which are moving in a straight line. So if the solid body is moving in a straight line and there is no rotation in reality for the solid body, then for that case, summation of moments at the center of gravity would be zero. So the body is in reality moving, okay, but the motion is in a straight line. Okay, so it's a solid body. We are not talking about a particle. It's a solid body, but moving in a straight line such that actually the rotation along the center of gravity is actually zero. So summation of moments will be zero, but these two equations will be there as it is. Now you have to understand one thing here, that suppose I have a body here. Let's say this is the body and the body is moving in a rectilinear motion. And so when the body is moving in the rectilinear motion, so I can say that there are no moments at the center of gravity. Summation of moments at the center of gravity is zero. But that does not mean that the summation of moment at any other point will also be zero. Okay, so when the body is in a rectilinear motion, then the summation of moment at the center of gravity will be zero, but at any other point the summation of moment might exist there. Okay, but in reality what happened is that the body is not rotating because the summation of moments at the center of gravity are canceling each other. So so that's why the body is not rotating. But if we are not finding the summation of moment at the center of gravity, if we are finding the summation of moment at any other point other than the center of gravity, so then the value might not be zero. The thing will become more clear when we start solving the problem. Okay, so let us have this problem. The cart and its load have a total mass of 100 kg. So this is the cart and the load. So the total mass of this cart and the load is 20 is 100 kg. So that's the total 100 kg, which is actually acting at the center of gravity. Determine the acceleration of the cart and the normal reaction on the pair of the wheels. So obviously the wheels are there on the floor, so there will be normal reaction on the wheels. So we need to find out the acceleration of the cart and the normal reaction on the pair of the wheels at A and B. Neglect the mass of the wheels. So basically a force is applied of 100 Newton at the handle of this cart. Okay, for that force, the angle is given as 3, 4, 5 is this triangle, which is mentioning what is the angle for this force. Okay, here this handle is like 1.2 meter from the floor, and from this from the handle to the center of gravity of this This object, the distance is 0.3 plus 0.4. This wheel B is at 0.3 distance. Between wheel B and wheel A, it's 0.4 and 0.6. And the center of gravity of this object from the floor is actually 0.5 meter. So anyways, all the dimensions are provided here. We need to find these things. So let's see the solution of the problem. So the first thing is that we need to do the summation of forces. So one thing is very clear, that the object is moving in the x direction. Since the object is moving in the x direction, so summation of forces in the y direction will be equal to 0, because there is no acceleration in the y direction. That is 0. Okay, so we'll have in the y direction, we have NA and NB acting upward, and the weight of the object is acting downward. And also there is a component of this force which will be acting downward. Okay, so it will negative 100 into 9.81 and negative 100 into 3 by 5 equals to 0. So we got this one equation, NA plus NB is equals to 1041. Is this a step clear or not? Okay, then let's do the summation of forces in the x direction. So summation of x equals to magx. So in the x direction, there will be an acceleration. Obviously, this will not be 0. So we'll have magx, and this is the ag that we need to find out in the question. Okay, so what are the forces in the x direction? In the x direction, this is a y direction force. This is also y direction force. This is also y direction force. So we'll only have a component in the x direction for 100 Newton of the force. So that is 100 into 4 by 5 is equals to 100 into ag. So if we use this, we're going to find out that the acceleration ag is 0.8 meter per second square. So by using the summation of forces in the x direction and using the summation of forces in the y direction, we find out ag, but still NA and NB are unknown. We have two normal forces which are unknown, so summation of forces in the x and the y direction was not able to determine the normal forces. So now what do we need to do? So since we know that the body is in in a linear motion, okay, so it's in a rectilinear motion. So we know one thing, that summation of moments at g is 0. Okay, or we can, what we can do is that we can find the summation of moment at any point other than that. Okay, so suppose if we, let's say if we find the summation of moment at nb, okay, this thing will not be 0, but one thing is very clear, that when we are taking the summation of moment at nb, so the nb will be ignored, and we can actually find na. So you can see the solution here. So let's say that okay, let's say here we are taking the summation of moments at A. So summation of moment at A will be what? So we have the weight which is acting at G. This is, okay, let me make it a little short. Okay, good. So we have G here, which we have weight here, which is acting at G. So this is going to have a moment along at point A. So it will be 100 into 9.81. Let's say we consider counterclockwise positive. So it will be positive, 100 into 9.81 into 0.6. Then NB will have a moment, but this moment would be clockwise. So it would be negative. So it will be negative NB into this distance, which will be 1. Then we have this force, component of this force. We'll have component of this force in the x direction, component of this force in the y direction. So the component of this force in the y direction will have a moment positive. So it's 100 into 3 by 5 multiplied by this distance. So it will be 0.6 plus 0.4 plus 0.3, that will be 1.3. And then we will have a component of force in the x direction, and it will have a moment across point A, and that would be negative 100 into 4 by 5 into 1.2, because this complete distance is 1.2. Now, summation of all these moments, this thing will not be zero. Why? Because summation, although the body is in the rectilinear motion, the summation of moment across G will be zero. But we are taking the summation of moment not across G, we are taking the summation of moment at A. Okay, so these things will not be zero. This thing will be equals to, previously we used to have like summation F is equals to MA. So here we'll have summation M is equals to MAD, MAD. Okay, so the mass into acceleration into the distance, because the object will be moving in this direction. So the acceleration will be across this direction, in the x direction. Okay, at the center of gravity. So this acceleration will have a moment arm at A, and it will be in the negative direction. So that's why we have a negative sign here. This moment arm will be, the moment will be acting in the negative direction. So 100 into zero point 0.8 into 0.5. So now we have this one equation where we can directly get what is NB. Okay, so here once we have NB, we can substitute this from here to here to find what is NA. Before moving forward, do you understand the solution of the problem or not? You can solve the problem the other way as well. Here I took the summation of moments at point A. You can take the summation of moments at G. If you take the summation of moments at G, then equals to, it will be zero. Right now I put equals to, not zero. Okay, because we were not taking the summation of moment at G, we are taking it at the summation of moment at A. Similarly, you could solve the problem by taking the summation of moments at B as well. This will be totally fine as well. Okay, so if you use the summation of moments at B, then in that case an A will be there, and then you're going to find an A from this equation and then substitute NA here to get NB. So there are three methodologies of solving the problem. Okay, after doing the summation of forces in the x and the y direction, either you can take the moment at B, or you can take the moment at G, or you can take the moment at A. Here it is done is by taking the moment at A. In the book, how it is done, in the lecture slides, it is done by taking the moment at G. In the lecture slide, that is done by the same problem is done by taking the moment at G. And you can also do this problem by taking the moment at B. So you can take the moment at B, A, or G, all will give you the same answer. But if you take the moment at G, then summation of moment will be zero. If you take the moment at A or B, summation of moments will not be zero. Although the motion is rectilinear, but summation of moments will not be zero at A or B. Rather, it will be equals to MAD. Okay, and likewise I have done here. So MAD, so MAD, and the negative or positive sign depends upon how the moment arm is being made across that point where you are taking the moment. Is there anything which is not clear in the solution of the problem? Please ask. Okay. After that, we can have another problem here. Okay, this is classwork problem number 4. The door has a weight of 200 pound. This door has a weight of 200 pound and the center of gravity at G. Determine how far the door moves in 2 seconds from starting from rest. If a man pushes on it at C with a horizontal force 30 pound, also find the vertical reactions at the roller A and B. So door is held by the rollers at A and B. Okay, so the weight of the door will be acting in the downward direction, and the reaction, normal reactions at A and B will be in the upward direction. So they two cancel each other and keep the door at the same elevation. The man is pushing with the force F at this point C. Okay, all the dimensions are mentioned here. And if the door was initially at rest, so after 2 seconds, we need to find out how far does the door moves. We need to find the distance. Okay, and the force with which the man is applying, the force which is being applied by the man over the door is about 30 pounds. The door has a weight of 200 pounds. Okay, so it's again the similar problem as we did before. So we can go through the solution of this problem. Okay, so we can have summation of fx equals to magx. Again, we have only the force of this of the force applied by the man over the door here. So it will be mag. So we're going to get what is ag. And once we have that, then we can take the summation fy equals to 0 because there is no motion in the y direction. So we'll have na plus nb minus weight equals to 0. So we got these two equations here. Again, we got ag, but na and nb are unknown. So now we need to take the summation of moments. This time here, I'm taking the summation of moment at g. Since I'm taking the summation of the moments at g, and since we know that the door is in the rectilinear motion, so summation of moment at g will be 0. So you'll have NA. Again, you need to specify one direction as positive. So it will be the counterclockwise direction considered, let's say, is positive. So NA will have a moment arm at G like this. So the moment arm for NA will be negative. And the moment for NB will be like this. So it will be counterclockwise. So it will be positive. Okay. And this force 30 pound, okay, will have moment like this at G. So this is also positive. So here we have now another equation for Na and Nb. So we have two equations here. For Na and Nb, we can simultaneously solve the two equations to find what is Na and Nb. So this is how we solve the problem. This problem where I have solved it here in my own handwriting, taking the summation of moment at G, in the book or in your lecture, it is solved by taking the summation of moment at A. So just so that you have, you can see that the same problem can be solved by taking the summation of moment at A or B or G. You can solve it by any way, okay? And all will give you the same answer. So once you have this, so you can find what is the distance traveled, because let's say assume that the acceleration is constant in the x direction because the force is constant. So for constant acceleration, we have this equation. We can just substitute the values and you can get what is the distance traveled by this door. Okay, is there anything within the solution of the problem which is not clear to anybody? Please ask. Is there anything within, is everything clear so far or not? Okay, I think we're going to stop here today, and inshallah next week we're going to continue with chapter number 17, and most probably next week we're going to finish chapter number 17. Actually, you know, we are going a bit fast in the sense that uh, we started in the very first week. Normally what happened is that the first week is normally lost. So the students are not totally registered and we are not able to start properly. So first week is normally lost. Also, I used to give break in the weeks whenever we have exams, but for your batch, the week when we had the exam, we also took the lecture. So right now, like for example, we're going to continue till chapter 18. So we have one lecture for chapter 17 left, one lecture for chapter 18 left. Well, right now we are in the 10th week, 11th and 12th. By 12th week, we will be finished. So suppose if we had missed our first week, and suppose if I had given you the break for the week when we had the midterm exam, so then we would have stretched till week number 14. But right now, in reality, if we continue like that, we might be able to finish by 12th week. So actually after this week, after today's lecture, two lectures are more left, and after that your course is finished. So we are not going to cover chapter 19 and other chapter. We're going to cover till chapter number 18. Okay, student is asking, doctor, what are the chapters that will be included in the second midterm? I don't know. I need to discuss it with Dr. Salim, and then we're going to finalize it. I know that you did chapter number 12 and 13 in the first midterm. So second midterm, most probably chapter number 14, 15. I don't know chapter number 16. We're going to add it or not. Depends upon the pace with which he's going with his class, with his group. Okay, for us, we are already done with chapter number 16. We have started chapter number 17. Next week's actually we're going to finish chapter number 17 as well. So our pace is quite fast right now. So we will see that what is the pace of Dr. Salim and what are the things that he has covered in his section. And then we see that what are the material that we can put for the midterm. So chapter number 14 and 15 will be there for sure. I'm not sure about chapter number 16. This we will be sure once I discuss with him. Okay. Uh, is there any update about our grades? This is another question one student is asking. I couldn't understand about that. What do you mean by that? Is there any update about our grades? Sorry, I couldn't understand your question. Please try to make the exam 2 chapters. Okay. So I will ask him and we will discuss that. Let's say that we make it only chapter number 14 and 15. But right now, I do not guarantee. But anyways, we're going to let you know. So far regarding the grades, we do not have any discussion yet. Actually, I was also very busy. Dr. Salim was also very busy. So in reality, we didn't meet at all throughout this period. But anyways, don't worry about it right now. Let's continue with the pace we are going in. Okay, and inshallah, in the end, we're gonna see what is best, what could be done. Okay, if anybody want to ask anything, you can ask. Otherwise, I think the time's up. We're gonna finish our lecture. Okay, thank you.